in our last section, we looked at finding the area between two curves, or the area between an x-axis and a curve. In this section, we're going to take this process one step farther and look at what happens when we create something called a solid of revolution. A solid of revolution happens when I take a region like this and I turn it around an axis. And you can see here this little symbol means that I'm going to take this region and turn it around the x-axis, creating a solid which looks something like a football. And we call it a solid of revolution. Okay, in your textbook, there are two equations for solids of revolution. One for rotating around the x-axis, and the other for rotating this way around the y-axis. Okay, you should add those two equations to your reference booklet. But let's take a look at this particular curve and the formula and see how that works. So since we're rotating around the x-axis, we're going to start with this equation. Volume is equal to pi times the integral from a to b of r of x squared dx. Okay, and looking at our picture, we can see r of x represents the radius here. R of x is the radius of a particular slice of that solid. And dx then would be the width or the height of that little section. And when we take all of them together from a to b, we get the volume pi r squared times that thickness. Okay, so for this case, my curve is f of x is equal to the square root of sine x. And we're going from 0 out to pi. So 0 to pi. And we always start with a pi out here. And then I need r of x squared. Well, r of x, the height of this rectangle goes right up to the function. So I'm going to have the square root of sine of x squared dx. Okay, what's the square root, or what's the square root of sine of x squared? It's just going to be sine of x dx. Okay, and then the integral for sine of x is negative cosine x. So I've got pi times negative cosine x evaluated from 0 to pi. So now I'm going to have pi and negative cosine x at pi is going to be 1, and negative cosine x at 0 would be negative 1, but we're going to add it since we would normally subtract there. And so we get 2 pi for our volume. And that's problem 1, example 1. In this next example, we're going to once again take a region and rotate it horizontally, but this time instead of rotating it around the x-axis, we're going to rotate it around a different line. So that changes our equations just a little bit. Okay, when I graph this, I can see that my endpoints, my limits of integration are -1, 1, and +1, 1. Those are the intersection points. And so these will be my limits of integration. For this top curve, f of x, the equation is 2 minus x squared. And then the axis of rotation let's call that g of x, is going to be g of x equals 1. Okay, so then our radius, our r of x, is going to be 2 minus x squared minus 1, which of course is 1 minus x squared. So that's what we'll be using for r in this problem. So let's set up our integration. Volume's equal to pi times the integral from -1 to +1, 1 minus x squared dx. Okay? When I multiply this out, I'm going to get 1 minus 2x squared plus x to the 4th. And now I can integrate this. So I'm going to have pi out here times everything. And this is going to be x minus 2x cubed over 3 plus x to the 5th over 5. And we're evaluating from -1 to +1. Okay, so my values for 1 would be 1 minus 2/3 plus 1/5, and subtract the values for -1, which would be -1. This will be -1, but the negative there will cancel it out, so it's plus 2/3, and then this will be negative minus 1/5. And when we work that all out, we end up with 16 pi over 15. In our next problem, we've got this region that's got curved edges on both sides. And we can't really rotate around either edge. We're going to rotate around the x-axis. Okay, the result is not going to be a solid. It's going to look more like a cup or a cone that has an empty space in the middle. So we're going to have to find the volume of the entire rotating area and subtract out the hollow space. So we'll start with this curve, which is going to form the outside of our solid of rotation, y equals the square root of x. And then this other curve is going to form the inside, part that we're going to subtract, y equals x squared. Now in the diagram, we've defined this part out here as capital R, and capital R, the outside radius, is equal to the square root of x, and little r is that other part, the inside, that we're taking away, which is x squared. Okay. Our cross section, when we cut this, is going to now look more like a washer than an actual disc. So we call this the washer method. There is an equation on page 357 that you should add to your reference booklet for the washer method. Let's continue now and solve this problem. Let's start now with our equation. Volume is equal to pi times the integral from a to b of r of x squared minus little r of x squared dx. So substituting in the values for this particular problem, we're integrating from 0 out here to 1. So 0 to 1. R of x is the square root of x, so I've got square root of x squared minus little r is x squared dx. Multiplying those out, I get from 0 to 1 just an x here minus x to the fourth dx. Now I can integrate this is going to be x squared over 2 minus x to the fifth over 5, evaluated from 0 to 1. Well, I know when I evaluate at 0, this is going to be 0 and this is going to be 0. So I only need to evaluate at 1. So I've got pi times 1/2 minus 1/5, which is going to give me pi times 3/10. In our next problem, we're going to be looking at this shape, which actually has two parts. We've got a solid base, or a disc-shaped base, and then the top part is more like a cup. So this might be like a glass that has a very large solid base. Because I've got the two different regions, I'm going to integrate in two different parts. Okay, and I've got a couple rules written up here. When y is in between 1 and 2, my outside radius here is r, and my inside radius is the square root of y minus 1. That's this curve. When y is in between 0 and 1, my outside radius is 1, and my inside radius is 0, because this is a solid base. So I'm going to now use two integrals to evaluate this. We're going to have pi times the integral from 0 to 1. And we'll do this base part first, 0 to 1. And we're going to have 1 squared minus 0 squared dy. And then my second part is going to be pi times the integral from 1 to 2. And we're going to have 1 squared minus that inner radius, which is the square root of y minus 1. This part also squared dy. Okay, this simplifies. And I've got pi times the integral of 1 dy plus pi times the integral from 1 to 2. This one's from 0 to 1. When I multiply this all out, I get 2 minus y dy. Because this was going to be 1, this is going to be y minus 1, and when I subtract it, then I get the positive 2 there. Okay, I'm going to go ahead and take the pi all the way out here. The integral of this is going to be y evaluated from 0 to 1 plus 2y minus y squared over 2 evaluated from 1 to 2. So I'm going to have pi times all of that. Okay, finding the values now. This is going to be just 1. This one, when y is 2, I'm going to have 4 minus 2, and then I'm going to subtract the values for y at 1, which is going to give me 2 minus 1/2. So this negative and that negative is going to make this a plus 1/2, but I've got 4 minus 2 minus another 2. So those three things cancel each other out, and I end up with 1 minus 1/2, so pi over 2. I'm sorry, 1 plus 1/2, because I've got minus and minus, so 3 pi over 2. In this last example, we're going to take a region here that does have a straight edge, but we're not going to rotate around that straight edge. We're actually going to rotate about the x-axis, which is 3 units away. So we're going to get a shape here that looks something like a bead with a hole through the center. Okay, so we're going to start with the things that we know here from the picture. R of x is equal to this expression, square root of 25 minus x squared. Little r of x is right here, so that's going to be constant at 3. So starting with my equation, volume's equal to pi times the integral. And I'm integrating from here at -4 all the way out to +4. Okay, I start with big R of x, so square root of 25 minus x squared minus 3 squared dx. Okay, when I take that square root and square it, I'm just going to get 25 minus x squared, and then subtract the 3 squared, which is 9. So now 25 minus 9 is going to give me 16. So I end up with pi times the integral from -4 to 4 of 16 minus x squared dx. I'm going to integrate that and get pi times 16x minus x cubed over 3, evaluated from -4 to +4. Okay, when I substitute the -4 and the +4 in there, I come up with 256 over 3 times pi as my volume. Okay. These examples should cover all the problems that you will see in your homework. And so we'll stop at this point.